Right, so now we're going to start looking at the low energy effective actions for the various superstring theories. And we're going to be so first of all, so effective supergravity theories, which describe the low energy behavior of the theory and describe the massless degrees of freedom. So the three the massless degrees of freedom have consist of the following bosonic fields. There's the metric, the B field, and the dilaton, which is there for all the theories as a common sector, plus for the 2A theories, 2A string theory, the low energy supergravity action has a vector field, which I write as C1, saying it's got one index, and a three-form or third-rank antisymmetric tensor gauge field. The 2B, there's a naught form or scalar, a two-form or second-rank antisymmetric tensor gauge field, and a fourth-rank antisymmetric tensor gauge field. And this is one whose field strength, which is a fifth-rank antisymmetric tensor, which is self-dual. And for the type 1 and the heterotic theories, there's a vector field in taking values in the Lie algebra of a gauge group K, which we've seen is either SO32 or E8 cross E8. And in addition, there are fermionic fields which consist of a gravitini, the superpartners of the graviton, together with spin half fields. But I won't go into details there. And as we've mentioned, the second rank antisymmetric, the second derivative action, supersymmetric action describing these fields is unique in each case. So these are the basic ingredients, and we can look at the dimensional reduction. So the dimensional reduction, if we take, for example, a three-form antisymmetric tensor gauge field, this will give rise to a third-rank antisymmetric tensor. So compactify on an N torus, there'll be some second-rank antisymmetric tensors. There'll be N of those because alpha will run from 1 to N. There'll be some vector fields, and because it's antisymmetric, each of these runs over N indices, so there's N minus 1 over 2. And then finally, there are some scalars, alpha, beta, gamma, N minus 1, N minus 2 over 6. So there's similar stories which happen for the two form, the three form, the four form, and so on. So in each case, each index can be either a space-time index or a torus index, and that way we get a multiplet of vector fields, antisymmetric tensor fields, and so on. And when you compactify on a torus, so compactifying on Minkowski space across an N torus, so the total dimension is 10, so this has got dimension 10 minus N. The resulting theory, if we consider, say, 2B, the 2B supergravity compactified in this way, if we look at the effective theory we get by assuming all fields are independent of the torus coordinates in the way that we've described, the resulting theory turns out to have, rather remarkably, turns out to have a rigid symmetry under the action of a group G, and the scalars are take values in a coset space G over H. So this is going to be the moduli space where G is a non-compact Lie group which will necessarily contain the group ONN, the T-duality group that we saw before, and H is the maximal compact subgroup. And because it's a symmetry, we see that all fields are in some representations, transform as a representation of the group G. So now, so let me give a table listing the groups for the very different values of the integer n. So if we consider, so we're considering 2b compactified on an n torus. So we'll consider different values of n, and then we'll tabulate the group which arises. So for n equals 0, there's the group SL2R. 1, it's SL2 for 2, it's SL2R, SL3R, 3 is SL5R, for 4 it's SO5, 5. For 5, it's exceptional group E6. For 6, it's exceptional group E7. And for 8, it's the exceptional group E8. And if one goes further, one ends up looking at infinite formally one is looking at infinite dimensional Lie groups, E9, E10. So these are the ones which arise, and if we look at the number of vector fields, so if we look at the vector fields A mu, the number of these which arise in each of these dimensions, the 2B theory has none. Dimensionally reducing, you have sorry, let's 3, which are in, and here you have, sorry, find the page in my notes. Here you have, sorry, sit back, 6, here you have 10, here you have 16, here you have 27, here you have 28, and in 3 dimensions, all the vector fields can be dualized to scalars. So there are, it doesn't, so a lot of the formulae don't quite apply there. And if we look at the corresponding charges, the electric charges in each of these cases, these transform in the 2 plus 1 of SL2. Here these can transform into the 2, 3 of SL2 plus SL3. Here they're in the 10, the 16. Here they're in the fundamental representation of E6, which is the 27. And here we have the 56, which consists of 28 electric charges and 28 magnetic charges. So here we see that the kinds of charges which these the kinds of charges which these fields can carry all fit into representations of the group G. So how should we say this? So the charges, the electric charges are all quantized. For example, in 4 dimensions, there's a familiar quantization that if you have a theory of both electric and magnetic charges, there's a quantization of the electric and magnetic charges. And there's generalizations of the arguments leading that to in all of the higher dimensions. In a lattice, and if the string theory has states carrying all these charges, then this will break the duality, the symmetry, down to the subgroup of G preserving that lattice. So this is something we've already seen in the case of the emergence of T-duality, where we saw that the momenta of the Kaluza-Klein modes was given by an integer, a quantized charge, which was the quantized charge of the vector field, which comes from dimensionally reducing the metric, and the winding modes, which coupled to the vector field, which came to the dimensional reduction of the B mu nu field of the antisymmetric tensor gauge field, were quantized, given topologically quantized, given the winding number. So those charges were integer valued, and as a result, the group ONN acting on those charges was broken down to the subgroup which preserves that lattice. So if we choose a basis for the lattice such that the charges were all integer valued, then it will that will mean that the only matrices will be that will preserve that structure will be integer valued matrices. And more generally, if we had a different basis for the lattice, then we get an isomorphic structure to that which I've just described. So that's a rather general picture. It's interesting to have a look in detail and see how this arises. So before doing that, let me just also, so this is the groups which arise from the 2B on the N torus. I should also want to, so for type 1 or heterotic, the group which arises from compactification on the torus turns out to be on Tn. We get a supergravity theory coupled to super Yang-Mills, which has got a group invariant under a group which is O n plus 16 cross R plus for n less than 6, and it turns out to be equal to O622. Same formula as here, but the R plus is enhanced to SL2R for n equals 6. And in other words, compactification on a 6 torus down to 4 dimensions. Here we see that the group clearly contains ONN, but it has some extra structure. So this, in the heterotic case, the T-duality group in fact extends to O622 or ONN plus 16, and this can be understood entirely within string perturbation theory. But in this case, there's an interesting group which is arising here in four dimensions, which is SL2R, which turns out to be an interesting group acting through electromagnetic duality and giving a strong weak coupling duality, and this is known as S-duality. So what I want to do now is talk about some examples which illustrate this general picture. And in doing this, I want to first look at compactification down to 4 dimensions, which of course is an interesting dimension. So so compactification on T6 to 4D. So if we start off with 2B, this gives rise to n equals 8 supergravity in 4 dimensions, which as I've already mentioned, has got 28 vector fields A mu. And if we take the type 1 or heterotic down to 4 dimensions, we get n equals 4 supergravity plus n equals 4 super Yang-Mills. And what I want to do here is I want to choose a point in the moduli space where the expectation values of the various scalar fields spontaneously break the super Yang-Mills symmetry, which in 10 dimensions was SO32 or E8 cross E8, gauge group in which this is broken down to an abelian group. U1, and it turns out that the number which arises is 28. So if we break all the gauge symmetry, then you end up with a theory with 28 vector fields, and which transform as the 28-dimensional representation of the group O622. At other points in the moduli space, or in other words, for different expectation values for the scalar fields, this group can be enhanced to a non-abelian group. So, for example, it could be enhanced to SO32 cross U1 to the 12, for example, which is what you'd get from direct dimensional reduction without turning from the SO32 string in 10 dimensions, but without introducing any expectation values. So in each case, we've got 28 vector fields. So we've got 28 electric charges and 28 magnetic charges. So I want to, just for the moment, just focus on one of the vector fields which arises here. And I want to look at one of the vector fields which arises in the, which arises from the n equals 4 super Yang-Mills. So for the super Yang-Mills with U1 28, sorry, that's so that's slightly differently. For the super Yang-Mills, there's a typical action which is of the form 1 over g squared integral f squared plus a theta term, which is the integral of f dual. So the dual means that if you've got a second rank antisymmetric tensor, so if you've got a second rank antisymmetric tensor x mu nu, its dual is given by taking x rho sigma and hitting it with an epsilon symbol, mu nu rho sigma, and a half there. So this means that you've got two f's contracted with an epsilon tensor, if you like. And this is the theta term and the Yang-Mills kinetic term. And in this case, it's useful to introduce a complex scalar, which is theta plus I over g squared. There's some factors of 2 pi, which and factors of 2, which I'm suppressing in all this. And so we have a coupling constant, which consists of this coupling constant, which takes values in the real line, and this angle, this quantity theta, which it turns out to be an angle. If you change this by 2 pi, then this term changes the action by an integer, which 2 pi times an integer, which leaves, once we've put the right factors of 2 pi and so on in here, and as a result, that e to the I times the action is invariant, and so the quantum theory is invariant. And so that for that reason, this theta is an angle. If we look at the heterotic string, or type 1 string, we get a similar story, but now we get e to the minus 2 phi f squared plus another scalar chi times f dotted in with dual f. So we see that so as expected, the expectation value of the dilaton, or e to the minus 2 phi of the dilaton, gives rise to the Yang-Mills coupling, and there's another scalar field which arises as the dual of the two-form field B mu nu, in a way which I'll describe in a moment. Another scalar field whose expectation value gives us this theta angle. And now here we can define tau equals chi plus I e to the minus phi, minus 2 phi, and this is becomes a complex scalar field whose expectation value gives this tau here. If we look at the field equations, we have that grad mu of star f mu nu, which normally would be 0, but we can modify that to introduce a magnetic current. And we have the field equation, which I'll write as d mu of g mu nu equals j nu, where this is an electric current. And if you look at this action, because there's this term in the action, we can define, if we define g mu nu as ds by df mu nu, we see that this is equal to e to the minus 2 phi f mu nu plus chi star f mu nu. In this case, or in the Yang-Mills case, you get this with the e to the minus 2 phi replaced by g squared and the chi replaced by theta. So the field equation is then given by this, and on the right-hand side we can have an electric current, and for a static configuration, the zeroth component of this will give rise to an electric charge density and a magnetic charge density, which you can then integrate to define the electric and magnetic charges. So we get from the integral of J0 and magnetic charges for the integral J0 tilde. And the SL2 SL2R that I've been talking about acts as 2x2 matrices A, B, C, D, which act transforming such that F and G transform as a doublet, and as a result, so this will call these little q and this little p, and as a result we have that so I think star F I want here, and then as a result we have that the magnetic charge and the electric charge also transform as a doublet, and tau transforms interestingly by fractional linear transformations of the form plus b over c tau plus d. So these are the transformations, and now if so the quantization of Q and P, if the electric and magnetic charges take values in a basic lattice, so that we can choose, if we choose units, that these take values in the integer values, so that if we look at Q and P, the only allowed values are integer valued points on the plane, then SL2R acts as a linear transformation on this plane, and we see that the charge by the SL2Z subgroup, the subgroup of integer valued matrices in SL2R. And a particular example of this is the matrix where we have 0, 1, -1, 0. This is a matrix which has got determinant +1 and is integer valued, and so is an element of SL2 and is invertible as its inverse is integer valued. So it's something which is an element of the group, and this acts to take Q to minus P and P to Q. So it interchanges electric and magnetic charges, and it also takes tau to -1 over tau, which, if theta equals 0, implies that the coupling constant goes to 1 over the coupling constant. And so we see that this is a strong weak coupling duality, which interchanges weak coupling to strong coupling and interchanges electric and magnetic charges. So let's have a look and see what that means in a bit more detail. So we have BPS states with charge Q and P in principle. There'll be electrically charged states and magnetically charged states. And I mentioned earlier that there was a Bps mass formula which gives the mass of these things in terms of the charges, and this turns out to be given by m squared equals g squared q squared plus p squared over g squared. So if we look at weak coupling g less than 1, we see that states, BPS states with charge Q0 are light, and the ones with charge 0p are heavy. And these these are realized as the W bosons, the massive BPS states, which and the supermultiplet containing the W bosons, and which will be electrically charged, whereas these are realized as magnetic monopoles. In the Abelian theory, there would be singular direct magnetic monopoles, but in this context, we're looking at a theory with non-Abelian gauge symmetry spontaneously broken, and as a result, there are non-trivial solutions of the Yang-Mills Higgs system, Yang-Mills scalar system, which give completely non-singular magnetic monopole solutions based on the Atuf-Polyakov monopole solutions. So we see that when G is much less than 1, the states carrying these charges Q and 0 are the light states which are part of the fundamental degrees of freedom, and these are heavy states which are realized in this theory as being states which are corresponding to solutions of the classical field equations, which in this case are the magnetic monopoles. So there are soliton solutions. These are regarded as soliton solutions in the sense that they're non-trivial classical solutions. But nonetheless, because they're BPS, the solution is unmodified by any quantum corrections, and so we can argue that there will be really the existence of these soliton solutions will mean that there should be states carrying these charges in the theory. So what happens is we now take the strong coupling limit as G tends to infinity for G large. So now states with so we had this mass formula here. So now if you had so now the states carrying the charge P, if G becomes large, the states carrying P, the magnetic charge will become light, and the charges with Q carrying the electric charge Q will become heavy. So now charges 0p will become light, and charges Q0 will become heavy. And the interpretation is that we're seeing that the theory is realized as a dual theory, which again is a super Yang-Mills theory, or super Yang-Mills coupled to gravity. But now the charges, the states carrying the charges 0p, which for weak coupling were interpreted as solitons, are now interpreted as W bosons of the dual theory. And the charges, states with charge Q0, which are now heavy, are the solitons of the dual theory. So what we're finding is that if we try and look at the theory for large values of G, we can try and look at it as a perturbation theory in 1 over G. And if we do that, we find the dual theory is again a super Yang-Mills theory, or super Yang-Mills coupled to supergravity, or embedded, which in our context is embedded within string theory. But this dual theory is one where the states which were fundamental degrees of freedom at the weakly coupled theory have those states with those same charges are extrapolated to states which are interpreted as solitons of the dual theory, and the solitons of the low weakly coupled theory are now interpreted as and continued to states which are fundamental degrees of freedom, the W bosons of the dual theory. So we have this rather remarkable story where the dual description, in this case, is again a super Yang-Mills theory. There's we say that there's an S-duality. This is an S-duality, which relates to strong and weak coupling regimes. So the is referred to as S-duality, and it relates solitons to fundamental degrees of freedom. And a key part is that given a state a BPS state in the weakly coupled theory, it extrapolates to a state with a BPS state with the same charges in the strongly coupled theory. Or put rather more in a slightly more general context, if you have a BPS state at one region of the moduli space, then it can be extrapolated to a BPS state at other regions of the moduli space. And one slight qualification here, we're talking about BPS states which preserve half of the supersymmetries. In some cases, the BPS states preserving less supersymmetries, the story can be a little more complicated, but we won't talk about those here today. And here I've been focusing on just one of the vector fields. In the case of the heterotic string compactified down to 4 dimensions, there are 28 of these vector fields, and so each of these charges, there'll be 28 electric charges and 28 magnetic charges, and they'll be transforming in this way under these charges. So now, and in particular, there's also we have a symmetry which is SL2Z across the T duality group 06 22 Z. And we have charges Q alpha P alpha, alpha goes from 1 to 28, so that these are in the 228 of SL2 cross 0622. The T duality we talked about before, and the SL2 acts as this electromagnetic duality we've just been talking about. So let's now look at the 2B compactified on T6, and again there are 28 Q alpha and 28 P alpha, because there are 28 vector fields. And these are acted on by this group, this rather mysterious group E7, which is broken down to a discrete subgroup. But there's a subgroup we can understand, which is the T duality group 066. And the conjugate, the complement of this is the maximal compact subgroup, which is an SL2R group. And under this, the 56 charges, the 28 electric and 28 magnetic charges, decompose into 12,2 plus a 32,1. So the 12,2 is rather like what we've just seen. The 12 consists of 12 electric charges and 12 magnetic charges. And these are ones which come from, so in the case of the superstring, I mentioned that there are fermionic degrees of freedom on the world sheet. And there are two possible sets of boundary conditions the fermions can satisfy, because the string is a loop moving through space-time, and the fermions on that loop can be either periodic or anti-periodic. The periodic ones are called Raman boundary conditions, and the fermionic ones are called Nervius-Schwarz boundary conditions. The antiperiodic ones are called Nervius-Schwarz boundary conditions, and the different boundary conditions give rise to two different origins for the vector fields. The 12,2 consists of the ones coming from the so-called Nervius-Schwarz sector. There are left-moving fermions and right-moving fermions, both of which are antiperiodic on the circle. And then there are the 32,1 are in the so-called Ramond sector. So this 32-dimensional representation is rather remarkable. This is a spinor representation for 06,6, the non-compact subgroup. And the Q and the P set in arising in the 12,2 are in a set of doublets of SL2, and so it acts a bit like we saw from for the n equals 4 case. So here we've got n equals 8 supersymmetry in 4 dimensions, and here we have the mass squared goes like, I'm suppressing some details, so we get but we get g squared q squared plus 1 over g squared p squared. So here q is a 12 vector, and this q squared means that we're taking a norm with respect to an 066 invariant norm, which in fact involves using a metric which depends on the scalar fields. But I'm suppressing those details here just to give the general structure. And if we choose to call these charges R, there are 32 of them, and these turn out to have masses which don't depend on the coupling at all in this frame. So here we're seeing that we're getting a generalization of this formula. So here we're seeing of the formula we saw before. So here we're seeing that the SL2 here is acting as an S duality, interchanging these electric and magnetic charges, taking G to 1 over G, but is leaving this sector strangely invariant, which came as a little surprise. So in this context, these are at weak coupling. These, as you'd expect, are arising from fundamental degrees of, might have expected, arise from fundamental degrees of freedom. These are magnetic charges arise as solitonic degrees of freedom. And these are arising in some other way. And so if, so this picture, so if all types occur, so we've got Q, P, and R, they take values in a 56-dimensional, they would lattice, they would all be quantized, and they would break E7 down to an integral subgroup E7Z, which is known as a U-duality group. So as we've seen, it contains a T-duality and an S-duality, but it also contains transformations which are more general and will not be ones which either are perturbative, which is the 066, or ones which are strong weak coupling dualities like the SL2, but will include transformations which will lead to much more general actions on the moduli space and relating rather different regions. So at the time of the work which was done in 94 and 95, my work with Paul Townsend and Ed Witten's papers, when we're talking about the n=8 supergravity, and it was realized that there would be solutions of the supergravity equations carrying each of these charges, which would be black hole-like solutions, but it was not understood whether all of these, whether or not there were states in the string theory which carried these charges. And subsequently, it was realized that the R charges do occur in string theory, and they're in fact carried by what are known as D branes. And one of the big breakthroughs was the discovery by Polchinski that D branes necessarily part of string theory. They allow more general boundary conditions for the strings, and these D branes in string theory give rise to states carrying these Ramond-Ramond charges. And this argument led to showing that there, and arguments based on this led to the establishment that there really are states carrying these charges, and lead to an understanding of the duality symmetry working in this way. So let me just say a few very brief comments about branes, including D branes. But if one has an antisymmetric tensor, AM1 to AM. Actually, let's just start off with a two-form antisymmetric tensor, BMN. Then its field strength will be HMNP, which is grad BNP. And the free field equations would be grad M HMNP equals naught, or more generally, you could introduce an electric current NP. And we can also define star H, which will have, in d dimensions, will have d minus 3 indices, and there'll be an equation grad star H mu m1 to m, and that's called d minus 3 little d, which will give couple to a current which normally would be 0, but we can introduce a magnetic style current, which will be have indices m2 to md. So this will have d minus little d minus 1 indices, or d minus 4. And j naught I, so if we have a time index and a space index, will be an electric current for will give an electric current which is carried by a string-like object which will be extended along the ith direction. And this would couple to something which had, so you'd have j tilde naught, then m1 up to sort of I1 up to I. So we've got d minus 1 here, so we go d minus 2, so we get to d minus 5. And this would couple to something which would, the volume, something which had a d minus 5 volume. And this is, so in 10 dimensions, this would have 5 indices, and this would be an extended object which was extended along a 5 plane along these directions. And one can show in the supergravity theory that there are solutions which carry these charges. In particular, there are solutions which are string-like solutions which couple to this 2 form, and there are 5 brane solutions, extended objects which extend not just in one direction like a string, but in 5 directions, giving what's known as a 5 brane, and which would naturally couple to, should be naturally magnetically charged with respect to this form. And one could go on in this way. We can, if we consider the third rank antisymmetric tensor, it would couple to something carrying 2 indices, extended in 2 directions, which would be a 2-dimensional object known as a membrane or a 2-brane, and its dual would be something extended in four directions in 10 dimensions, giving a 4-brane, and so on. So we can look at in each case at those objects, and in particular, we've seen that the 2A theory has a vector field which would couple to a particle or naught-dimensional object or naught brane, and a C3 which would couple to a 2-brane or membrane, and a 2-form field which couples to strings. And similarly, in the 2B theory, there's a C2 which couples to and a C4 which couples to 3 branes. Now these fields C1, C2, C3, C2, and C4 are all fields in the Ramond sector, and the branes which couple to these are in fact D branes. So they're realized in string theory as these objects which provide generalized boundary conditions for the string, which have been talked about in one of the other lectures in this Lonti series. So these gives the D0, D2, a D1 brane and a D3 brane. And all of the, and so in particular, the naught branes we saw in the charges we saw in 4 dimensions carrying Ramond charge arise from D strings and D3 branes wrapping the 6 torus, or from D2 branes wrapping the torus. So these are the electrically charged ones. There are also magnetically charged ones. We have a D4 and a D2, and here we have a D5, and this is self-dual, so we get the D3 again. So one can realize the 32. So if we think about, for example, on a 6 torus, we get the number of states from the D branes. We get from the D0 brane, we get 1 state, because there's from the D2 brane, it can wrap 2 cycles of the 6 torus. So there are 6 choose 2 ways of doing that, which is 6 times 5 over 2, which is 15. For the D4 brane, there are 6 choose 4, which is 15 again. And sorry, that should have, I wrote that there, that should have been a D6 brane. And from the D6 brane, we get 1. And then adding this up, we get 1 plus 15 plus 15 plus 1, which gives the 32 we were looking for. So we understand the 32 Ramond charges as arising from the various D branes of the 2A theory wrapped on the 6 torus. And you can also check that for the 2B picture, you can get it from the, understand it from the D1, the D5, and the D3 branes wrapped on the 6 torus. So in that way, we understand these charges as arising there. And so in this picture, we see that we understand the self-dualities arising of the theory as arising from subgroups of the symmetries of the low energy effective action. And the subgroup is a subgroup which preserves the BPS spectrum. The BPS states are lie laterally in a lattice, a charge lattice, so that the duality group is the subgroup of the supergravity symmetry, which preserves the lattice. So this leads to the conjecture that the duality symmetry of the theory includes, is given by this U-duality group G of Z. So in the case of compactification to 4 dimensions, this was the integer subgroup E7 of Z. So the integer subgroup E7Z of E7, which on a certain basis is one because the subgroup of E7 in which realized by integer valued matrices. So the conjecture that was made was that this is in fact a symmetry of the full string theory. And that is indeed what has been found. Sorry. So over the years, there's been a very large amount of evidence amassed to in support of this conjecture, and there's been a lot of these non-trivial tests really things which the theory has passed with flying colours. So I think that although the symmetry has not been proven, we've gone a long way to understanding some of the theory in this way. And this has some remarkable consequences. One is that if there is the U-duality symmetry, then the symmetry will relate states with the charges, the electric and magnetic charges that some of them, the electric and magnetic charges which we know must arise in the theory, for example, from momentum and winding modes of the fundamental string, and will relate these to these other charges, such as the Ramond charges. So if the duality is a symmetry, then it implies that if there are these the momentum modes and winding modes, there must also be states carrying all the other charges which you can get from those by acting with the duality group, in particular the charges which include the Ramond charges. And each of these charges, in turn, we understand as arising from branes wrapping around the cycles of the torus. And so this is an argument which says that if there is this duality symmetry, there must be these extended states in the theory, so that the duality predicts that there must be these branes in the theory, these p branes. Some are d brane. The ones coupling to the Ramond fields are d branes, but there are also the 5 branes which couple to the magnetically charged, ultramagnetically charged with respect to the 2-formed gauge field that I just mentioned. And so string theory is not just a theory of strings, but at the very least it contains strings and branes. And the fact that we've seen that there are duality symmetries which relate the string modes, the string charges to the charges carried by branes, means that in a sense the duality symmetries mean that all of these things should in some sense be on the same footing. There are symmetries relating them. So string theory, although at the perturbation at weak coupling, it looks very much like it could be understood as a theory just of strings. If one's looking at strong coupling, or more generally within the moduli space, we find that it necessarily is a theory not just of strings, but a theory of branes. So I'll stop there, and then I'll continue in another part of I'll continue in a moment in another part of the lecture, the next part of the lecture.